Oh, hi. Welcome to our virtual lecture. Today, I want to start chapter 3, ionic compounds and molecular compounds. And as usual, I will split the chapter into two sections, part A and part B. Please have a piece of paper or your notebook and a pen. There will be some examples or illustration I will show you during the presentation. Allow me to share my screen so that you can have a look at the PowerPoint slide as well as the whiteboard, which is my iPad in this case. Part 3 is on molecular compounds and uh, ionic compounds. When we say molecules and compounds, what does this mean? A molecule is just a compound which consists of two two or more non metals. You know, in the periodic table, we looked at the periodic table, how it can be broken down into metals, metalloids, and non-metals. Compound which consists of two or more non-metals are molecule, e.g. CO2. You see there is carbon, there are two oxygen. This is a molecule, examples of molecules. In parallel to this, I want to explain what is meant by formula unit. This is made up of metal plus non metal with metal. The fundamental unit of a substance or a compound consisting of a metal and a non-metal is called formula unit. For example, here we have sodium chloride, for example, is we have only one sodium and one chloride ion forming a compound sodium chloride. We call this formula unit, just to give you heads up between or drawing a parallel between a formula unit and a molecule. Now, this is the chapter outline. For part A, we will look at the hydrogen, oxygen, and water molecule. Section 3.2, we will look at the different types of chemical bonds, ionic bond, covalent bond, and metallic bond, just briefly. In section 3.3, we will look at how to represent chemical formulas and molecular models. You can recall for those who took into to chem lecture as well as the lab, probably one of your lab experiment, you had to build molecules using the molecular models. I do have with me the model. Let me just show you what is meant by the model so that you can have an idea of what it is. Maybe you cannot see, but here is carbon. There is green for chlorine and black for carbon. This to give you what is molecular model. And look at the atomic level view of element and compounds. And lastly, ionic compounds in section 3.5. I'll leave section 3. I mean part P. I'll explain later on this when we get to part P. Let's see how many different atoms or how many different substances do exist. How many different substances exist? If you are asked a question, are you able to list them down, like just give a large estimate? To answer this question, there are many elements that combine to form different compounds. So a compound consists of two or more elements, e.g., this is hydrogen, or we say here hydrogen. And by the way, you should be able to write the chemical name and chemical symbol. Oxygen, for example, here, this is an element with a chemical symbol O. These are what elements, which when they combine, they form compounds. When we say compounds, right here, includes, I think, SH2O, sodium chloride, they combine form compound. Sodium combined with chlorine. These are the compounds, elements. You see these elements, these are the elements on the periodic table, which you should be provisioned right now with the periodic table. Allow me to share. I think I do have here one of the periodic table. I had the periodic table, see right here. This is the periodic table of elements, and these elements, they do combine to form compounds. Look at this. By now, please memorize, commit to your memory the chemical symbols as well as the chemical names, because this will be in quiz number 2, which will be posted shortly. So going back to our slide on elements and compounds, note that compounds are made up of pure elements, and elements are those on the periodic table. They create diversity to answer the question on the many substances which exist. To create diversity of substances that we can find in nature is a direct result of ability of element to form what? Form compounds, which I've shown you here. Using the element hydrogen and oxygen, they can combine to form a water molecule, which is a compound in this case. Let's briefly look at the formation of the water molecule. Water molecule consists of two things, two elements: hydrogen and oxygen. If you look at these two elements, hydrogen and oxygen, they have dramatic differences in terms of chemical reactivity. For example, hydrogen is flammable, oxygen, of course, support combustion. But when they combine, they form a compound with different chemical properties as well as physical properties. For example, hydrogen is gas in nature. Likewise, oxygen is gas, but we know water molecule is liquid at room temperature. So when two or more elements on the periodic table combine, they form compounds. Underline the word compound here, how we end up with that. I always find students, they confuse between, they don't differentiate between an atom, an element, a compound, a mixture, homogeneous, it's all these terms or vocabulary throw you off in an exam. But here, a compound consists of two or more elements. Here is just the physical properties of water molecule in comparison with the two elements which form up that compound. For example, here boiling point of hydrogen gas, and by the way, the two spheres you see here indicates that in nature they exist as diatomic. This is hydrogen gas, which is diatomic, by the way, and oxygen. This is oxygen, not oxygen, but oxygen gas exists as diatomic. We have boiling point for both. You see boiling point for water. The point here is when elements combine, they end up with compounds with different properties. No one will actually ask you about what is the boiling point of water? What is the boiling point of hydrogen comparison to oxygen, right? Or the flammability of all this. The point here is when elements combine to form compounds, the resulting compounds have different chemical properties compared to the elements which form them. All right, there's a difference between mixture. We talked about mixture in the previous chapter, mixtures in comparison with compound. Mixture, compound, they have definite composition, whereas mixture do not have uniform composition. In a mixture, element can mix in any proportion. That means it's not uniform. For example, in the room where I am, I may have different composition of oxygen, hydrogen, but or even in a mixture of sand and sugar, it's not that they will end up being uniform. But in H2O, all right, the composition is uniform, element combined in fixed definite proportion. Remember the law of definite proportion, regardless of the source of a compound, always the element which makes up that compound is well defined. In other words, you will never see water molecule written like this or this and say this represent water molecule. No, this is wrong because we know always compound form or they have definite proportion. As in this case, we are looking at water molecule. Let's see, hydrogen, oxygen. That means you have oxygen here. Let's say in a closed container here, we have oxygen and hydrogen gas in a closed container. The mixture here have proportion of hydrogen can have in it. That means indefinite. You can have high percent of or high percent of oxygen or a high percent of hydrogen in comparison to the molecule. By contrast, water molecule is composed of one oxygen and two hydrogens. What that means is just interpreting the chemical formula for H2O. And it could be in liquid form. All right, this is just illustrating the definite proportion is well defined. We covered extensively in the previous section the law of definite proportion. Law of definite proportion. This is just a pictorial representation. I can blow up this. This is pictorial representation of elements, which is a mixture, and a compound, which has well-defined proportion. For every one oxygen we have, there are two hydrogen. This is just liquid H2O, and this is a mixture of hydrogen and oxygen. Please draw a parallel and understand that there's a difference between mixtures and compounds. Moving forward fast, just this leads us to our chemical bond, and what we call chemical bond. Please take note of this chemical bond is simply defined as a strong electros. This is all static force of attraction. This is a attraction between two or more atoms. If you are asked to define what a chemical bond is, it's just a strong electrostatic force of attraction between two or more atoms to form compounds. At the outset, there are three types of chemical bonds. There are three types of chemical bonds. One, there is ionic bond. There is the covalent bond, and then there is the metallic, all right, metallic bond. There is the metallic bond. You have to know that there are three types of bond, and we are going to cover the first two here. This is what we are going to look at in this part, covalent bond and ionic bond. Chemical compounds are composed of atoms held together by either one of the three types of common bonds you will cover in this course. And simply a chemical bond is a result of attraction, a divine electrostatic attraction between charged particles, electron and protons that are composed atom. I want to just highlight what is charged particles. It could be sodium and chlorine, all right, fluoride ion. When sodium metal loses its one electron, it becomes positively charged. Chlorine, when it gains one electron, becomes negatively charged. Recall how we predict the ionic charge using the periodic table for main group. We know from classical physics that positive and negative do attract. Positive, positive repel, right? Negative, negative repel. So if I represent that, I can have sodium here and a positive and chlorine negative here. This is the force of attraction here. There is the force of attraction between the two. And that is what is highlighted here, that charged particles will be any other metal, it will be any other non-metal with an overall negative charge. We're going to talk about the cation and anions later on. I know some of you may remember that. So chemical bonds can either be ionic covalent, all right? It can be ionic covalent. These are the most common type of bond you need to read, make your own notes. You can use any other resource to make note on this until you commit your memory. So here is the ionic bond. What is an ionic bond? Ionic bonds occurs between metals and non-metals, underlying metals and non-metals. You may not know, all right, an element, but let me just show you by now. You should be able to classify an element as a metal on this side. You see these metals and non-metals on this side. You should know where they are. You may not know this is bromide, right? Bromide ion, or maybe between K and Cl, all right? This is a metal, and this is a non-metal. Anything on this region and except hydrogen are non-metal. So that when we talk about the metal and a non-metal, you should know where they reside. And this involves transfer of electron. Transfer of electron in the sense that sodium will lose one electron. You will see an arrow in some text with E, meaning that an electron has been lost by sodium, and chlorine gained that electron, forming an ion negatively charged, leading to the force of attraction. And here, this is where we talked about the what we call ionic. This is ionic bond. How do I know that? Because there is a metal and a non-metal. This is metal, and this is non-metal. You see, metal and a non-metal, and an electron is being transferred. It's not always that one electron is transferred in an ionic bond. Calcium will lose 2 electrons to become positively charged. Aluminum will lose 3 electrons to become positively charged, +3. Please revisit the predicting ionic charges using the periodic table. That's how ionic bond is formed. Metal atoms tend to form cations. And what are cations? When I talk about cations, and anions right here. These are positively charged particle. And this is negatively negatively charged particle, negatively charged particle. E.g. here we can have calcium, it can be potassium, it can be lithium, Li positive. This could be O2 negative, F negative, and 3 negative. I'm using the periodic table to predict this, you know. Don't think that I've memorized based on the position on the periodic table. I should be able to determine the charge based on the group number. You should always do the same thing given the periodic table. So know what an ion is and the cation are positively charged. They form what we call ionic bond. This is a learning check to show if you understand. You may see a question like this in the exam. Ionic bonds are formed between non-metals, metal and a non-metal, metals or metalloids. You know, metalloids, those are elements which lie along the staircase, along the zigzag line on the periodic table. Please revisit that. The correct answer for this question is B, metal and a non-metal form what we call ionic bond, ionic compound, all right, that means a compound formed by metal and a non-metal is composed of lattice. That means it has regular dimension of alternating cation and anion, So in other words, what is meant by this is alternating, it could be positive here, that is what is meant by alternating, all right? I'm just alternating the colors to illustrate the lattice. And maybe when I come here, it will be this, and this, and this, and this. You see how it's alternating, and this, and this. And then I can have this, and this. There is alternating what? Alternating regular cation and anion. This will be positive, this will be negative, positive, negative, positive, negative, and so forth. It's a lattice structure. Common example is the sodium chloride. This is this is how the alternating positive and negative, the cations. There is a message here. You need to understand this is the sodium metal, this is the chlorine gas. Look at the size of chlorine compared to the size of sodium. They are in natural state, but when an electron is transferred from sodium to chlorine to form chloride and sodium ion respectively, the size of a cation being formed is always smaller than the parent atom. The size of an ion, that is an ion negatively charged, is always larger than the parent natural element which form that time. And the alternating positive negative form lattice structure with regular alternating positive and negative. This is sodium chloride. And that is, in reality, how the atoms of chlorine and sodium are arranged in sodium chloride salt. How is ionic bond formed? You need to understand that ionic bonds are formed as a result of transfer of electrons. I showed you in the previous slide how electrons are transferred. This is the transfer of electron. It could be transfer of 2 electrons. It could be transfer of 3 electrons, and so forth. So the point here so far is ionic bonds are formed as a result of transfer of electrons. Sharing of electrons, this is a covalent bond. Just to keep you, draw a parallel between ionic. We'll come back to covalent ionic bond and covalent bond. We are going to get to this in part P. So sorry about that. I was just drawing the parallel here. So this is a transfer. Please remember transfer of electrons. I'm going to abbreviate electrons like that. And this is formed by sharing. We just put that this is sharing of electrons, sharing of electrons. So that's what we have for that. The correct answer for this is C, transfer of electrons. Now, let's see, covalent bonds are formed between 2 or more nonmetals sharing electron. I explained that, and they form what we call molecules. For ionic bond, they form formula units. Formula units, just to highlight that on my PowerPoint slide here, formula units, smallest. The smallest unit is called formula unit. That is, if you take 1 chlorine and 1 sodium, put them together, that's the fundamental compound. We call that formula unit. Here, smallest unit here is called, that's what we are talking about right now. The smallest unit of covalent compound is called molecule. Molecule, this is what is mentioned here, that composing a molecule. E.g., if I take 2 hydrogens here, if I take 2 hydrogens and 1 oxygen, it forms a molecule. If I take 1 sodium and 1 chlorine, it forms a formula unit. So that these terms right here, formula unit and molecule, can be confusing to some people. Please understand what they mean, so that when you see this, a molecule, it's a compound formed between 2 or more nonmetals sharing. There is no transfer of electron. There is no transfer of electron for that. They form what we call a molecular compound. All right, so here we have a molecular compound. Sometimes we call this molecular compound. Okay, so here is just an illustration of the sharing of electrons between 2 nonmetals to form that. This is a conceptual question, which I think it's in the text. All right, what type of bond or ionic bond between metals? No, what type of bond, ionic or covalent, between that formed between nitrogen and oxygen? I will look at the position of the nitrogen, oxygen, and remember this is something we covered in the previous section. All right, one is naming the elements and knowing the chemical symbol for that. If you don't know the chemical symbol for nitrogen, how will you classify it as a metal or a non-metal? If you don't know the chemical symbol for oxygen, how will you classify as a metal or a non-metal? Please go back and learn that. I was even thinking of giving you a quiz on spelling of chemical symbol only. Otherwise, it might come back and haunt you. The correct answer for this is covalent, because nitrogen is a non-metal, oxygen is a non-metal, and the type of bond between them is called covalent what? Covalent bond. And it's formed as a result of sharing of electron. Representing compounds, section 3.3, how do we represent compounds, chemical formulas, and molecular models, all right? We will look at the chemical formula, indicates the elements present in a compound and the relative number of atoms or ions in each. Here is an example of a compound, aluminum chloride, for example. I've been using H2O. Let me use a different compound here. This is the chemical formula. This is the chemical formula, and you should know what indicate. This means we have one aluminum and we have 3 chlorine atoms. You should be able to indicate the relative number of atoms. The 4 here applies to hydrogen. You read this as 4 hydrogen and 1 oxygen. This is the chemical formula. Sometimes you may have parentheses. For example, here I can have Mg3 TO4 like that. You should be able to understand what is going on. This is magnesium phosphate, and here we have 3 magnesiums. And the subscript here applies to everything in parentheses. You read this as 2 phosphorus and 8 oxygen. The 2 does not apply to magnesium, by the way. These 3 as well, the subscript only applies to magnesium, but does not apply to phosphorus or the oxygen. So here you read as 2 phosphorus and 8 oxygen. I can have iron 3 hydroxide. For example, this is iron 3 hydroxide. Just the way we did this, you have 3 oxygen and 3 hydrogens and only 1 iron. These are chemical formulas. And here is H2O, which indicates that we have 2 hydrogens and 1 oxygen, or sodium chloride. Sodium is 1 and chlorine is 1. Carbon dioxide, we have 1 carbon, 2 oxygen, and so forth. So you should be able to interpret a chemical formula. Our chemical formulas can generally be categorized into 3 different: 1, empirical formulas, molecular formulas, and structural formulas. You should be able to differentiate between the 3 formulas: structural, all right, molecular, and empirical. Empirical formulas, all right, keep the relative number of atoms in it. It's the simplest, whereas the molecular keeps the actual. I want to illustrate relative and actual so that you understand what is meant by relative. Here is a dinitrogen. We will come back to this tetraoxide for here. And it indicates that we have 2 nitrogens and 4 oxygen. There are 2 nitrogens and 4 oxygen. Empirical formula here is molecular formula. And here is the empirical formula, okay? So if you look at here, it's saying relative. It's just the simplest whole number ratio, I'll say, for empirical. Molecular keeps the actuals. You see, I have actual. If I simplify by 2, this will give me N or 2. You don't express empirical formula with fraction. It's got to be whole number. So I'm just gonna divide it by 2. If that, I can have for benzene C6 H6, dividing it by 6 through, this will give you CH, and this is the empirical formula, It's not that always all compounds have different empirical formula from the molecular formula. Sometimes empirical formula can be the same as the molecular formula. For example, there is nothing going to change here. CH4, CH4 is not going to change. You can't simplify any further. You cannot have fraction, okay? Please take note of this empirical formula. If you divide by 2, you have what? You have HO dividing it by 2. Here, this is dividing it by 2. CCl4, the only common factor for this is 1. So do not just try to end up or divide everything by 2 always to end up. It's not true that you divide by 2 to get the empirical formula, but it's got to be the simplest whole number ratio. So structural show the connection. For example, here is, let's go back here. I can show you the empirical formula for CH4. This is the or empirical formula. All right. Structural shows the connection. You see, uses lines to represent covalent bond, the sharing of electrons. See, you see this? It is bonded to 4 hydrogen. By the way, you should know how to write. We're gonna come back to that, but you see, we have what? We have used lines to show covalent bond, the sharing of electrons. Here the lines represent what we call covalent bond, which is sharing of what? Sharing of electrons, all right? Sharing of electrons. That's what's meant by covalent bond. It can be conveniently, it can also convey the molecular geometry. We look at the molecular geometry in chapter 8 or 9 down towards the end of the course. We will look at the molecular geometry in details. Here is H2O, right? I mean peroxide. This is the structure of peroxide, not H2O. And you see the connection between the atoms in peroxide. Well, depending on what we want to convey, we can use any of the formulas. However, a structural formula communicates the most information, and empirical formula communicate the least empirical. Like structural, you can tell the molecular geometry, you can tell whether the molecule is polar. We will talk about the polarity down the line, but the empirical formula doesn't help you in determining whether the molecule is polar or non-polar. I'll come back to that just to point out that the structural formula for compounds communicates the most information we may need. Here is a question, a conceptual question, 3.2. Select a structural formula for each of the correct answer. You see, everybody knows that. You should be able to write the structural formula for each tool. What is keep the empirical formula for deca? This should have been decapoene, I believe, but nevertheless, we have been given the formula, and what we need to do, this is pH, by the way, it is P. If you can see, there is 10 here, and then hydrogen, we have 14. You have to use the simplest, okay? You have to use the simplest ratio here. If I divide by 2, I divide by 2. This will give us P 5, H 7. This is the empirical formula. To end up with that, you just divide by what? Divide by 2. Divide by 2 to get that. Representing molecules, I know some of you may have built the molecules before. And what I'm holding here is this molecular model of, I was trying to make, I'll say methane, CH4, but I don't have all the balls and stick. All the balls and stick. You have used a stick before, you see this is bending. I can remove. You see, I can have the two, you can see there is a ball here, there is a stick. I can form bond between the flag, all right? Just to show you the molecular models, we'll cover in details down the line, but this one specify completely how it's shown. But remember, chemists use color coding to represent atoms. You will see, or you can recall, in pole and stick, where the ball represent atom, the stick can represent the chemical bond and sharing of electron, and always the color coding will remain the same. When you look in the text, hydrogen is represented by a white sphere, carbon black sphere, and of course, you can recall they have 4 holes for carbon. Hydrogen has 1 hole representing the valence electron. Remember that. So learn, you will see that in future, the color coding represent the actual what? The actual atoms. They are color coded to specific elements. So it will never change. Always oxygen will be red. From the previous illustration of mixture and compound, using H2O, recall water molecule, there was 1 red sphere and 2 white sphere, which represent hydrogen and oxygen. Hydrogen and oxygen. This is space filling, really. Will you see this? Is just using the methane to illustrate the difference between molecular formula, structural formula. We use using lines to represent covalent. This is balls and stick, which you may have seen this in the lab, or you will see this in the lab in one of the experiments. And lastly, space filling model, right? Lastly, space filling model. Conceptual question, you can read this. This is about the ball and stick, and the correct answer is each sphere represents the electron cloud of an atom. The nucleus will be too small to see on the scale. Ways of representing compound, please learn, understand the difference between empirical formula, molecular formula. Notice when we divide by 2, it will give you the empirical formula. Empirical formula can be the same as molecular formula. We can divide by 2 and further. Don't assume that to derive or determine the empirical formula, you need to divide by 2. If you divide by 2 here, it will give you a fraction, which is not the correct way of representing the empirical formula. That's all. Read more on this, representing molecules. At an atomic level view of element and compound, this section 3.4 elements may be either atomic or molecular. What do we mean by atomic? That means it can just be by itself, especially group 8 elements. Let me just represent that or show you the difference between atomic. Group 8, helium, argon, krypton, xenon, because they are not diatomic, all right? These, they do exist as atoms, all right? They exist as atoms, atomic. It's an element. Look at this on the periodic table, an element, and I'll just show you what constitutes the group 8 here, neon. All right, these exist as elements on the periodic table. Helium, neon, argon, krypton, xenon, and radon here, they exist as what? They exist as element based on what we just talked about here, that elements may either be atomic, they exist as atoms. It's not only what I give you here, we can also have neon, Ne, by the way, this is neon. No, Ne, random, for example, give you that. While molecules are molecular compounds, molecular elements, There are 7 diatomic you need to know. 7 diatomic elements. These include hydrogen, oxygen, fluorine, nitrogen, and this is oxygen. No, not oxygen, but this is what? This is hydrogen. You have to know hydrogen. What this is? Hydrogen gas. You're gonna be seeing cars. They are diatomic. This is oxygen. What? Oxygen gas. This is fluorine. Please remember to spell it correctly. Fluorine gas. This is neon gas, like that. Neon gas, nitrogen, not neon. Why am I saying neon? This is nitrogen. Nitrogen. Sorry about that. You need to know. And then there is bromine, PR2. This is liquid at room temperature. Liquid. All right, it's liquid at room temperature. And iodine, this is iodine, and it is solid at room temperature. Where am I going with this? These are diatomic. When we say molecular, they are diatomic, maybe either molecular or ionic. So if we look at here, there is, how do you classify the pure substance element? Atomic, example, neon, I just gave you that. Neon, the group 8 falls right here. Molecular compound, oxygen, I gave you just, it's not only oxygen, by the way. It's not only oxygen. Right here are the 7 diatomic molecules I gave you here. And that one will fall under the example of molecular elements, right, in molecules. And then compounds, which means 2 or more elements combining together can be molecules, 2 or more nonmetals coming together, or ionic compounds, metal and a non-metal. Please remember that, make your own notes so that you know when you are given a compound, you should be able to either classify as molecular compound or covalent compound. By the way, we call, let me just bring this to your attention, molecular compound, all right? Or this is the same as covalent, by the way. They are the same, they mean the same thing, covalent compound like that. It's the same thing. They are made up of what? They are made up of non-metals. And then ionic compound, of course, we'll come back to that in details. We'll come back to that. So those two terms can be used interchangeably. I've given you the examples of elements, which include, it can be at atomic level, sodium, neon, potassium, magnesium. Look at how I'm just reading this. Sodium, neon, potassium, magnesium. You should also know the first 50 elements you'll be given. You'll see in the exam chemical symbols. And if you don't know the names, there's no way you can proceed with that, especially when we get to balancing the equation. If you don't know what it means, it's going to be a challenge for you. Yeah. Please remember that. Use 4-6 index cards if need be. Back to our slide, molecular compounds do not normally exist in nature with single atom as either basic unit. Instead, they exist as molecule, 2 or more atoms bonded together. All right, these are the 7. Look at, let's count. 1, 2, 3, 4, 5, 6, 7. And you should be able to name them. Look at my whiteboard. I do have the names. Hydrogen gas, oxygen gas, fluorine gas, nitrogen gas. They exist as diatomic. This is liquid at room temperature, and this is solid at room temperature. Some exist as polyatomic element. Poly means more than one, such as sulfur or phosphorus. All right, this is the periodic table. Molecular elements, they have been highlighted. I can blow up this so that you understand what's going on with this slide. Elements that exist as diatomic. That means in nature, we have H2, N2, O2, F2, Cl2, all right? Element that makes it as polyatomic ion are just right here. Selenium, sulfur, and phosphorus, all right? So that's what we need to know. Now, our learning check problem, N2, Cl2, and O2 all exist as what? The correct answer is A, diatomic molecules. It's not ionic bond. Some of these you can just use elimination method to get the correct answer. Also, as I explained about the atomic molecule, you see they are the same, and here I see this represent a pure element which exists as diatomic. All right. Classify the substance represented by the molecular view shown here. This is a conceptualized. Sometimes I like question which you have to think. This is critical thinking. We don't know what it is by the fact that two spheres bonded together represent a molecular element, molecular compound. I know if you don't draw, if you don't pay attention to the fine print, as they say out there, you will say, what is the difference? They look alike. But if you don't know the difference between an element and a compound, you just double guess yourself. This is an element because it represents the same thing. If I had, let's say, green and red, that will constitute a molecular compound, such as H2O we looked before. There was two white spheres bonded to one red sphere. That is a molecular compound. Molecular compound, that's what I look at it. All right, the basic unit of molecular compound is called molecules. Remember that there was a slide which I gave you about the formula units for ionic compounds and the for molecular compound, the simplest form of molecular compound is molecule. So understand that the constituents. Give a new molecule, molecules, all right, propane and so forth. Last section on part A of the lecture is now we're going to look at the ionic compounds. And ionic compounds are composed of cations, usually metals, and anion, usually non-metals. You should be able to determine whether an element will form a cation. Generally, metals will lose electron to form cation. So a cation plus anion, negatively charged. By the way, right here, I know we're gonna come back to that. Let's see. What I wanted to show you here is what we mean by cation. Cation, we will come back to this. This is positively charged particle. It is positively charged particle. And you know where they are. Please go back to chapter 2. You will see how you can use the periodic table to predict the ionic charge for main group elements, And then anions, all right, anions right here, they are negative lowered. These are negatively charged particles, negatively charged particles. And this includes, I think, as O2 negative, F negative, Cl negative, N 3 negative, or P3 negative. You should be able to use the periodic table to predict those. I'm just using the main group so that you understand what is meant by cation and anion, please use the periodic table to predict the ionic charge. I explained the basic unit. The simplest form of ionic compound is called formula unit. If I can take one sodium and one chlorine, put them together, I'll end up with what we call the formula unit, which is the simplest. And the two are electrically neutral. They cancel each other. I'll come back to the simplest way of keeping track of all this, one element to another element. Going back to the periodic table for main group element, and remember numbering of the groups, the vertical column on the periodic table using the American convention system using the number and a numeral. I mean, a number and a letter A representing the main group. Those they do have what? Predictable ionic charge. When atoms of main group or representative elements, you can predict whether it's slow. Metals tend to lose. You see, these are slow. Group 1 will lose 1 electron to form positive 1. Group 2 will lose, except for beryllium. They lose 2 electrons to form cations with an overall charge of positive 2. The most common one in group 3A is aluminum form positive 3. Please remember this as well for sulfur, selenium, tellurium, fluoride, chloride, bromide, and iodide. All right, those are the common ones. You need to use the periodic table. Cations are formed when at least 1 electron is lost. It can be 2, it can be 3, to form monoatomic. All right, where we are going mono, what we mean by mono, let me just come back to that word. Why we are saying mono is we have what we call, let's say, ions here. These are charged, we say charged particles. All right, these are charged particles, and it can be, and I think I gave you this earlier on. It can be anions. It can be cations, or it can be here polyatomic ions. We would come back to this, but it's good to put things in perspective so that when we move forward, you will make a connection between what you learned previously and where we will be. Cations include such things as Na positive, Ca2 positive. We covered in the slide, you can see from there, this can be negative, N3 negative, P. If you see, these are right here is what we call monoatomic, so that you know what is meant by mono. It means 1. In comparison to what is out there and what is coming down the line, these are a group of atoms. I'll say polyatomic ions right here. These are a group of what? Group of atoms which are bound together. All right. Together, they work as one. The most important thing is they have overall what? Overall charge. They have an overall charge. E.g., you need to learn right away. I know you can recall previously. Just give you example. There is an overall charge. -2, it could be O negative. So that when you say mono, there is what we call polyatomic ion. We're gonna look at that later. Anions are formed when at least 1 electron is gained. Gaining, remember, electrons are negatively charged. So if 1 electron is gained, it's coming with its overall charge. We have monoatomic. when we say monoatomic, or when I say monoatomic here, that means it's only one monoatomic anions. Monoatomic anion. These are just examples of molecular anionic compound. These look like ethane 2 carbon chain, and then ionic compound, 2 nonmetals, 2 or more nonmetals, and sodium chloride. To understand this slide, A is C2H6. Structural formula C, and then 3 hydrogens here. You can count the spheres here, and you'll see that we have 1, 2, 3, and there are 2 carbons here joined together. This is A and B here. Sodium chloride is just NaCl. Calcium form an ion with an overall charge of what? This is calcium is in group 2. You need to use the group number. Please do not memorize the ionic charges. All I need to know is which group is calcium. If you don't know the chemical symbol for calcium and you're just given the periodic table with the chemical symbol, it's going to be difficult for you to draw a conclusion on what is the ionic charge. So if I look at this is in group 2, and we know all group 2 will form positive 2. All group 2 will form positive 2, and the correct answer is positive 2. It's not only that calcium, you have to just given the periodic table, anything on group 2 here. You see calcium, magnesium, strontium, and so forth. You have to commit to your memory the group number, all right? Group number. So the correct answer for that is D. For iodine, this is in group 7, all right? This will form negative 1. The correct answer is E. For this, it is D right here. For this, it is E. Please, again, I cannot stress enough, please learn the chemical symbols and the chemical names. Look at this problem right here. In the final exam, I'll just give you the name, and if you don't know the chemical symbol, you'll run into trouble. We are heading into balancing the equation, and if you don't know the name, I'm just going to be giving you the names, and I expect you, and even 1 year from today, somebody will expect you to remember these chemical symbols, and you know, it will be a challenge if you don't get it right away. The names and the chemical symbols and the position, and of course, how to interpret the periodic table, So summarizing the ionic compounds, ionic compounds, all right? Ionic compounds always contain positive and negative ions. Cation and anions is obvious. I guess you can read that. In a chemical formula, the sum of charges must be equal to the sum of, you don't need to memorize this bullet point here. We will come back to a better way of handling the total sum of charges in a compound. The charges for the charge of the representative element can be predicted from the group. That's what I just did, you know. I'll give you in the exam, in the quiz, in the exam, the periodic table. It will not have the charges the way we have been learning, but in this section, there is a periodic table with the ionic charges. You will not have that luxury in the exam. Please remember to use the periodic table for main group to predict the ionic charge. Representative, and again, these are the A's on the periodic table, the one we number using a number and a letter A all the way to 8A, or sometimes you may see this as 8A, it's the same thing, Roman numeral, or we can have 1A, and we can also have just 1 for IUPAC system, This is 18. This is just 1. All right. Please remember to learn the Roman numeral 1 through 8. This represent main group or representative. All right. Recall in the previous section, main or representative means the same thing. It means the same thing. Transition metals tend to form multiple charges. You know where the transition metals are. This is not all of them right here. Most of them, they form multiple charges. We will look at that and how we predict the charges for those using what you are given. Hence, their charges cannot. Please, for the transition metals, and even in a transition metal to some extent, do not use the periodic table to predict their charges. You have to learn that. I'll show you how to learn how to predict the charge for the transition metals. So naming ionic compounds categorized depending on the metal in the compound. Naming. But before we do the naming, we should be able, moving forward in all compounds, you can either be asked two things. Either name the compound given the chemical formula, or you can be asked to write the name given the chemical formula, which is on this section. I will show you how to, first of all, write the formula and then we name. Naming type 1 ionic compound, type 1 ionic compound. This is type 1, it should be type 1. I don't know if there is something wrong here. This should be naming of type 1 ionic compound. Type 1 ionic compound contain metal whose charge is invariant. What this means, it is predictable. So for main group, we can predict the ionic charges. It is bonded toward to a non-metal. This is group 1 right here for type 1, sodium and chlorine, for example. We will learn how to write the writing ionic what? Ionic formulas. For type 1, how do you write the ionic formula? The point here is use crossover rule. Use crossover rule. What does this mean, crossover rule? When you cross something, it's crossing, right? It's crossing. So that means you need to predict the ionic charge for each one of them, and then you cross over only the numbers, not the charge. So that this will be Na, the one is coming from chlorine, and there is a one coming from what? Coming from sodium. When there is one, you don't indicate that. It will just be NaCl. It is understood there is one. It's just like balancing the equation, if you can recall. We don't put one in front. We will come back to that. But it's understood that there is one here, which came from chlorine. There is one. So that's how we use the crossover rule for ionic compound. What I'm doing right now is writing the correct formula for type 1 ionic compound. Type 2 is the one with form multiple. So if I have calcium is in group 2 and oxygen is in group 2 like that, no, group 6 negative like that. If I cross over, I'll have calcium. The 2 is coming from, maybe I should have even used different colors here. Let me even erase this so that you see this is O with the 2 negative there. And I can erase this so that you see where that is coming from, Ca. And then, yes, And then 2 is coming from what? 2 is coming from oxygen. And then O here, and then the 2 is coming from calcium. You do not leave the way it is, but you can still subdivide by 2, and the correct answer for this is CaO. It's not always that you divide. If you can still simplify with the whole number, all right, without ending with fraction, it's allowed. Don't leave just 2 and 2. Likewise, for magnesium oxide, Mg, it's always magnesium oxide because of what? Because of Mg2 positive and O2 negative like that. So this is the correct formula for that. However, if you are working with something, let's say, for example, and let's see here, aluminum +3 and oxygen -2 like that for mono. This will be Al2 O3 like that. I'm using here the crossover rule. Here is the crossover rule in writing the correct formula for what? For type 1, all right, for type 1. So once you write that, you need to learn how to name the ionic compound. How do we name that? This is called sodium ion, and this is Cl. You change the ending to chloride, IDE, ion. And what you need when you have this, look at how you name this. That's why the title here, type 1, is bonded. You can read of this, and you say sodium. You always start with the metal, sodium chloride, not ion. We can read of ion. For type 1, the one with. So likewise for CaO, this one is, or rather, I'll have just started with this by itself. Ca2 positive. This one is calcium ion, and 2, this is oxide. This is oxide ion. So this will be CaO. This is calcium oxide. It's calcium oxide. So cancel that. That will go away. We have that calcium oxide. So you will name the metal always the same charge. The metal always have the same charge for type 1, by the way. That's what is meant by this. Metal ion always have the same charge. Same charge means it's not going to change. Always calcium will form +2, will never change. Sodium will always form +1. Potassium will always form +1. Fluoride will always form -1, phosphide, and so forth. That's what is meant by same charge. You can use the periodic table to predict the ionic charges invariant. That means it's not going to change. They will always have same charge. Look at what we have. And like I said, you not have this periodic table in the exam. Please learn to use the periodic table to predict the ionic charge. Always group 1 will form +1. Always group 2 will form +2. We covered that before. If you look at this, it's assumed that you have learned the type 2 ionic compounds. But let's look. Which metal has the same charge in all of its compounds? If I look at this is the transition metal. This is molybdenum. This is lead. All right, lead can form +2, +3. The only one here is strontium. This is group 2. It forms +2, and it's the only metal among the 4 we have here. We can form same charge in all of its compounds. So it's Sr for strontium. Please learn those names in the chemical symbol. This is naming of monoatomic anions. Anions are negatively charged, and take note of how the suffix is changed to IDE. Base name, you add IDE to form fluorine from fluorine to fluoride, from chlorine to chloride. All right, from iodine, remember this is F, this is Cl, this is Pr, this is just I, this is O, this is S, this is N, and this is, but when form ion, they form negatively charged based on the periodic table. And the most important thing is, how do you name them? All right, please do not say fluorine. I know some people, if I ask you what is this, some might say fluorine ion like that. No, this is wrong. You have to say fluoride, and then you add the word ion at the end. Oh, I'm just talking to myself. I was knew that this is the proper way. Not this. Don't say fluorine ion. I've seen students giving me and saying, oh, this is bromine ion, or this is iodine ion. It's saying iodine. Apart, this is just common. I want you to make your own notes on how you name these anion, monoatomic. Remember this mono, there is polyatomic, which is coming down the line as well. All right. All right, binary compounds containing only 2 different elements, the names of binary compounds take the following form. Take note of binary. Pi means 2, and it can be the name of the cation and the base of the name adding the IDE. And I give you an example, potassium chloride. Type 1, naming them, potassium chloride, just the way you name potassium, but you have to change the IDE, chloride. The name CO, calcium oxide, I gave you example on that, how you change the ending, learning check. Predict empirical formula for any compound that form from magnesium and fluorine. So here, what you need to do is, instead of predicting, you have to use the formula. What is the formula? The formula is cross over rule, crossover rule. All right, crossover rule. And the crossover rule, this will be Mg 2 positive, magnesium is in group 2, with the charge of negative positive 2. Fluorine or fluoride is in group 7. So writing the correct formula for this is you cross over like that, and the correct answer is Mg. You don't indicate the 1 from fluorine, but the 3 you see, the 2 you see here is coming from magnesium ion, and the correct answer is D. The point here is, have you mastered the crossover rule? Can you use the periodic table to predict the ionic charges? You should. Okay, you should. And the correct formula here is E. The correct formula is E. All right. Now, type 2 ionic compounds, that means those ions, the ions involved in this case form more than one charge, right? They are formed by those metals, the transition metals. What are they? Metals of this type are often transition. You know where the transition metals are? I showed you before. This is the transition metals right here. The transition metals are metals on this region. Some of them, they form more than three charged particles, more than three charged particles. And how will we move forward with naming them, or how do we know that? The metal charge must be specified for a given. So we will need to specify the charge. There is a need to specify the charge. Proportion of the metal cation to non-metal help us determine the charge on the metal. The full name of the compounds containing them form one kind. I guess this is how we will start using the Roman numeral here in parentheses, the base of the non-metal. Full name of the compounds. For this, you have to name the metal and the base using the parentheses to indicate that, to illustrate that iron, let's say iron, which is a transition metal, chemical symbol for that, it can be +2 or iron +3. How will you know which one is which? You name the ions using the Stokes system. Name ions using what we call Stokes system. And this one uses this system uses Roman, this is our Roman numeral, what is mentioned here, Roman numeral in Fahrenheit. To indicate the charge on cation, the charge on cation. So we have to indicate that. E.g. now, this one will be Fe 2 positive. We call this iron, we say iron, 2 ion. And this is 3, yeah, this is iron 3 ion, the Stokes system. We will come back to that. This is meant by here, so that if we have here FeCl2, you name this as iron 3 iron 2 chloride. This is how you name that. You name the cation first, indicating the charge on cation using the Roman numeral, the metal right here, and then you add the ending IDE, which is indicated here. Now, FeCl3, this will form, or this will be iron rather, and then the Roman numeral here indicates the charge on cation, then the word chloride, which is the base name for the anion, the non-metal in this case. This is just the general, it will take practice, guys, to really understand how to go about, all right? You have to learn, teach yourself how to use the crossover rule, how to use the Stokes system, the Roman numeral. Well, I wouldn't really worry much about the sum of the charges here. Just use the crossover rule. What is meant by that is, you know, the crossover rule is FeCl. This has, or rather, iron 2 positive, iron negative. So the crossover rule gives you FeCl2. You can cross over you can uncross using, by the way, you can uncross or take back the numbers to predict what the charge was so that you name. How do I know? at the outset, you should know that there is iron 2 or iron 3. It will never change. It's a question of memorizing that. Let me just have this right here. Iron 3 and iron 2. So this will be iron 2 chloride. The non-metals, it will always have a constant charge. It will never change. It's a main group element. So I know this is always going to be 1. But for a transition metal, you have to know or learn that there is iron 2, iron 3. And how will I know that which one am I dealing with? It's based on uncrossing that these two came from iron, and it can be iron 2. It can be iron 2. So you need to know that. Here we have been given sulfur, for example, has a charge of negative. Iron has a charge of positive 2 or positive 3, but sulfur has a charge of negative 2. Using the uncrossing over negative 2, if you look at this, you have to uncross. The 2 came from, so I know iron has positive 2, negative 3. I know the 2 cancel out from the empirical formula, leaving me this. So I know this is iron 2 sulfide. This is iron 3. If you uncross over, you're going to get that. Chromium, bromine is negative 1. There is no one here. You uncross, you end up with that. There is copper 1, copper 2. I'm going to show you that. This is type 2 compounds, by the way. All right. You need to learn those, how to predict the ionic charges. So I was saying that we use Roman numeral. This is the Stokes system. I recommend that you learn those common polyatomic ions, not polyatomic ions, but rather transition metals which form more than one charge particle. This is iron 2, iron 3. You will never see iron 4 or iron 5 or iron 6 or iron 1 or iron 6 or iron 7. These are the known charge particles formed by iron. So transition metals, you have to uncross wherever you are handling a compound so that you know. What I want to show you or share here is what you need to commit to your memory, know the ionic charge. When we say chromium 2, you should know the chemical symbol for chromium, Cr, and the Roman numeral indicates the charge on chromium. It's a transition metal. Chromium 3. This is an old way of naming them. The one with the least charge in that series ends with OUS, is Latin name. Chromic IC with the IS charge, you see this. Look at the ferrous, ferric, the one with the high charge. Cobaltus for cobalt, cobaltic. Cupric, cuprous. Look at the charges. Take note of mercury 1 is diatomic. Each one of them is bringing in positive 1, and we have an overall object, negative 2. So this is what I want you to learn, guys. The Roman numeral in parentheses indicates the charge on the metal cation. There is another way of, learning these cations. Some others which I gave you a different fashion here, shown on table 2.4, we may not have that in our text, is if you look at all the most common ions with an overall charge of positive 1. If this is easiest for you, you can do that and name them, all right? This is the only polyatomic ion with an overall charge of negative 1. How you name them? Ammonium ion. You can move on to positive 2. You see positive 2. And here we have mixed those transition and main group element. The key factor here of grouping this is based on the charges. Like if I want to know chi 2 and then chi 3, this is what we have. They're just grouping based on that. It could also, we have polyatomic ions here, but the most, what we are using or overwriting monatomic, polyatomic is the overall charge of negative 1, negative 2, and negative 3. Oh, just like in type 1, we use crossover rule. Don't try to do the summation of that. Using the crossover rule will just take care of finding the summation of charges. Using this example here to show you how crossover rule works is, let's see, just show you whiteboard right here. And the question is, the correct formula for iron 3 bromide is what? Do not memorize, do your calculation, derive the formula. And here, I will look at the cation iron 3, and this is iron 3, and bromide is negative. Use the crossover rule. Crossover rule indicates that we're gonna have that, and it will be F E P R 3. Look at how I ended up with the correct answer here, which is P R. It's B. This is F E P R 3. Some folks might think that the 3 is for iron, and they just put the 3 in between the 2 here and say this is correct. No, you gotta use the crossover rule. Earlier on, I highlighted the 3 categories of ions. There is the cations, there is the anions, and we have the polyatomic ion. Cations, anion, monoatomic, that means only one element. But polyatomic ions are group of atoms which work together, such as what? Such as sulfur. And please learn the chemical symbols as well as the formula. What I wanted to do is show you the series. Look at this. 4 oxygens and 3 oxygen. There is 2 oxygen with an overall charge of -1. There is NO3 with an overall charge of -1. There is PO3 with an overall charge of negative, and then there is PO4 with an overall charge of -3. You should be able to name. The reason why I'm bringing out this and drawing a parallel, putting them together, is in a series with the one with less number of oxygen ends with ITE. We call this phosphite, ITE, and this is phosphate. Look at the series, ATIT. You should be able to name that. This one has less number of oxygen. We call this nitrite. And we call this nitrate, ATE. Look at ITE. So I hear nitrate. There is here sulfate, ITE, and sulfate, ETE. Naming of polyatomic ions. In this slide, we just given few. This is very minimal on what you are expected. I wouldn't really matter even or worry about, what's going on here, trying to memorize, thinking that you may be asked about this table. The most important thing you need to learn, commit to your memory, is the naming system for most polyatomic ions. Let's look at the example here. If we have, I have given you nitrate, nitrite, sulfate, sulfite. This is the use of ATE, ITE. Teach yourself. You can devise your own method, the easiest way for you to recall this or to name the oxyanions. By the way, oxyanions is the same as saying polyatomic ions because most of them, they contain oxygen. We say oxygen, and then they are anions. That means most of them, they have an overall charge of negative, except few of them, such as ammonium, NH4 positive, or hydronium, H3 positive, if you look at that. This is common, table 3.4, common polyatomic ions. I want you to memorize, learn, use the periodic table. You should be able to know the most common, name them: hydroxide, nitrite, nitrate, chromate, dichromate, phosphate, I gave you that, hydrogen phosphate, dihydrogen phosphate, ammonium. You will see these guys, and probably I will not give you the polyatomic ion. You need to know this. You need to memorize. Okay, I know this is the basic thing, where we are going to this is we want to speak the language of chemists. We want to learn, we are now learning the alphabet, the 26 alphabet in English, A through C. You can write an essay on that. Likewise, where we are with this is learning the basic of writing the correct formulas for what? For compounds, learning them from the basic. So this is A, B, C, D. Learn them. Chemical formula, as well as the name, so that when you are asked to write the chemical formula for a compound, you will write the correct name, you will spell them correctly, all right? So oxyanion, if there are more than 2 ions in a series, then the word hypo meaning less, and then par meaning more than. Hypo and then par meaning more than. Hypochlorite, chlorite, ITE, chlorate and perchlorate. You can learn those. You may see in naming: hypochromite, chromite, and so forth. Look at how the series, how the number of oxygen is increasing. They all have an overall charge of -1, an overall charge of -1. So naming the compounds containing polyatomic ions. But first, writing the correct formulas, we use the crossover rule as well. What do I mean by that? Let me just minimize this. You see my whiteboard here. If I write the formula, use the crossover rule. Let's say calcium ion, which is +2, and hydroxide with an overall charge of -1. This is calcium ion, and this is hydroxide ion. If I use the crossover rule just the way we did before, don't worry about doing the summation of the charges. I'll bring down here, look at this, the 1 will come down there, 1 will come down there. This is where you use the parentheses. Do not just say C, or, somebody might say that this is what I do have when I do the crossover rule. The correct answer is the polyatomic ion hydroxide work as if it is 1, and you need to use the parentheses or 3 like that, or 2 or like that. And this is the correct, this is wrong. Just showing you how to write the correct formula for that using polyatomic ion. You can also have magnesium, in group 2. Phosphate is a charge of -3 like that. The crossover rule, this is polyatomic ion phosphate. So it's going to be Mg. The 3 is coming from phosphate, and 2 here, this is coming from magnesium. Writing the correct formula. And we name this as magnesium phosphate. Naming them. Now you name that. You have to learn that. And this one was, this right here is calcium hydroxide like that. Calcium hydroxide. So I have that. calcium hydroxide. Writing the correct formula for ionic compound containing polyatomic ion, we use the crossover rule as well. It could be K. All right, this has positive 1, and carbonate like that. This is carbonate ion. This is what? Potassium ion. K2, CO3. When we name this, you see, I'm using the crossover rule, by the way. I'm using the crossover rule. You do not use parentheses when it is one. I know you may say, why can't I use parentheses here and put a subscript one? No, don't use parentheses, or here use parentheses if it's only one, that is what it is. So here, this is potassium. Look at how I'm naming this, potassium carbonate, potassium carbonate like that. Then I have that, potassium carbonate when you name that. So sodium nitrate, N2, you see nitrite, not nitrate, nitrite. So it's assumed that you have learned mastered naming of polyatomic ions so that you can now name any compound containing polyatomic ions. This is a question on identifying whether you can recognize the compound with polyatomic ion between this and this and this. What are the polyatomic ion? This one has nitrite. This one has sulfate with an overall charge of -2. Again, you need to learn, commit to your memory the ionic charge. I always recommend that use 4pi6 index card either from Walmart, it's cheap, or from dollar store, $3. 4pi6 index card, have the formula on this side, have the name on this side. That's how you can teach yourself, all right? That's how you can teach yourself. Or sometimes you may try to download from App Store like polyatomic ion flashcard or whatever, whichever is convenient for you. Please check out that. Even the elements, periodic table naming them, you can look at the apps out there which are free. You can download for learning them as well. So here, there is the sulfate, and then there is the nitrate. We don't have this. This is not polyatomic ion. This is not polyatomic ion. This is not the correct formula for sulfate. This is not a formula for nitrite. Here is nitrite, and there is -1. Nitrate doesn't have -2. You know, if you don't learn this, you will think that, oh, they look the same, all right? But with thorough studying and committing to your memory, you will not make the mistake. And the correct answer is A. All right. All right. There are some compounds. There are some ionic compounds with water of crystallization incorporated into their formula. In other words, when those compounds are formed, there are water molecules, or maybe there is one water molecule, or maybe half a water molecule are included in the crystal structure of those compounds. We call them hydrates, all right? Hydrates are ionic compounds. Yes, they are ionic compounds. There is a metal and there is a non-metal, okay? Or there is a metal and polyatomic ion with some specific number of what? Specific number of molecules associated with each formula unit. We call those hydrates. You will see in one of the lab experiment, if you are taking the lab, or if you took the lab at UNF, one of the experiment, you will work with hydrates. Example is the Epsom salt. This is magnesium sulfate, and then dot. This does not mean multiplication. This means 7 water molecule is incorporated in the chemical formula. Quite often, in the lab, I see students when they are asked to find the molar mass of an hydrate, they find the molar mass of this portion of the hydrate, write it down, the total mass of magnesium, sulfur, and 4 oxygen, put it, and then they multiply by 7, and no, that's not, I know in mass, this means multiplication, but we do not multiply. Just to highlight that, what you need to do is find the molar mass of this portion of the hydrate, write it down, find the molar mass of water molecule, 2 hydrogen and 1 oxygen, and then you multiply by 7. The 7, you multiply by 7, the molar mass of H2, and then you add the 2 for this portion and for the 7 water molecules. That's how you find the molar mass of hydrate. Just to highlight that, because I know you need this piece of information, and they will expect you in the lab to have learned in the lecture. So coming back to our hydrates, all right, there is a systematic naming of these hydrates, and it has to do with the number of water molecules. You need to learn the prefixes used to indicate how many water molecules are in the system. Here we have 7, we use hepta for 7. Use index card to learn the hexa, the hepta, and so forth. These are the prefixes used to indicate the water or crystallization in the hydrate. Hemi is half. We call this calcium sulfate. This portion is calcium sulfate. And then hemihydrate, that means it has a half water molecule. This is hexahydrate. You just have to name, and I will call this copper 2 sulfate. I forget to say copper 2 sulfate. There is copper 2. Maybe to be specific here, let me just see if I can do some editing a little bit. Maybe it will require me to, I don't want to end the show, but remember there is copper 1, there is copper 2. So I'll say copper 2 because sulfate is -2. It cancels out with the +2 from sulfur. There is copper 1 and there is copper 2. And we are handling copper 2 in this case. So here, barium chloride hexahydrate based on this. Please memorize this. We will also need these prefixes in molecular compounds. Let's see, learning check real quick. What is the chemical formula for barium hydroxide? At the outset, how will you proceed with this? 1, you need, or you should be able to write the formula for barium hydroxide. This is how you'll write. Barium is in group 2, all right, +2. Hydroxide is polyatomic ion with a -2. So write the formula for that. We will bring down, do not say barium just with the subscript on hydrogen, but the subscript applied to both oxygen and hydrogen. Hydroxide is -2. This is right here. This is hydroxide ion. And this is barium ion. I'm using the crossover rule instead of doing the summation of charges. I know you may read in the text and talk about like the sum of the charges and you're trying to do the math. Let's just simplify by using the crossover rule. It will take care of finding the summation for that. And then here, octa. So you need to understand what octa means. Octa means 8, and there is dot here. All right, there is dot, and then there is 8, H2O. It is an hydrate, and this is how I name the compound. I'm just gonna show you how to end up with that, and the correct answer is, we forgot to put it as a subscript. This is wrong. I don't see 8. 8 cannot come in front, as if you are balancing the equation. There is no hydroxide here, so we use this, and I think the correct answer here is A. All right, the most appropriate answer in this is A. You can try using an elimination method in exam 2 and it will work. It will work. So, okay, this marks the end of part A of our lecture. I'll come back shortly to continue with part B.